My name is Pete Saronis. Welcome to our kickoff of the HPC Climate Change Working Group, however you want to say it. My name's Pete Saronis. I love connecting dots, building bridges. I was in government for a long stretch, but bringing people together and humanizing the individual, their passion, and talking about topics that are relevant both in government and in society is what we are hoping to convey today. And as we move forward, a few parking lot items again. For all of our guests and attendees coming in, we hope that you, one, are educated, informed, and enlightened today. We are the working group and project that falls under what was kicked off back in May, which was the Climate Change Summit. And those of you who attended in Western Virginia that day heard about this, and this is our first entree into meeting some of the amazing thought leaders that you will hear in a minute, and talk about a topic that is timely, obviously, and unpredicted when we were first putting together the agenda. It's titled Battling the Blaze. We're going to hit a little technology, people, and process. We have some great stories to tell, and we're going to get going here in a minute. For our, again, attendees, you will be using the chat function in this case to communicate, because we hope that you will have your ears open and eyes wide open to listen and observe from our guests. I want to give a shout out to our good friends at ACT-IAC who are helping make this happen. Mark Carkenny, Carol Miller, the HPC community leadership team, Miss Ann Duncan, Ron Butra, Robert Sears, and Frank Indiviglio. You will hear more about those folks as we build out this project and do more of these types of webcasts. The webcast, as you know, is being recorded. So without further ado, again, my name's Pete Saronis, and I will moderate and try to keep my mouth as shut as possible, because these are the folks that we hope you learn from and are excited to know moving forward. With that, I'm going to introduce a little bit each one of our guests, Miss Jennifer Mahoney, Mr. Robert Sears, and Mr. Ian Lee. I'm not going to read their bios because they're going to talk a little bit about their personal and professional journey and their passion. Robert Sears, Director of NWAVE at the NOAA, the National Oceanic and Atmospheric Administration's Enterprise Network Program. Say that 5 times. Amazing individual, a colleague and friend, and just so fortunate to have Robert here. Miss Jennifer Mahoney, Director of the NOAA Global Research Laboratory, staff of nearly 200 meteorologists, software engineers, and support staff dedicated to, I love this quote, making forecasts better. You'll hear a lot about GSL, its role with the mission of NOAA. And like I say, mission matters. There's a lot happening outside the Beltway. And lastly, and not leastly, if that's a word, Ian Lee, HPC security architect and security operations team lead in the Livermore Computing Division at Lawrence Livermore National Laboratory, one of our 17 treasures. And he's got a little geek in him, but a lot of passion. So you're going to hear from me and talk a bit too about the connection of Wildfire's cybersecurity for all of our techie inside the Beltway cyber folk, and the impact that HPC is having to drive innovation. So without further ado, Miss Jennifer Mahoney, the floor is yours.
Well, thank you very much, Pete. And hello, everyone. I'm Jennifer Mahoney, and this is really a fun thing to participate in. So I'd like to say thank you for this opportunity. Let's see. So I lead a research laboratory within NOAA, as Pete mentioned, the Global Systems Laboratory. And we are passionate about, talking about passion, building forecast systems that deliver solutions. So we are building tools, we are delivering them to National Weather Service operations, to external users that are interested in the tools and technologies we develop. Particularly, our specialty is high resolution modeling, so that'll get us into the HPC discussion as we move forward, as well as decision support tools, graphics, displays, and all of that. And my passion started when I was young. Being a meteorologist, you typically love the weather when you're 5. And so I was able to carry that passion forward through the laboratory and really participate in delivering some of the tools that the Weather Service now use to deliver all of the forecasts that the communities receive. So thank you very much, and I'll turn it back to you.
Well, thank you. And I'm going to pivot over here to Robert, but just I love knowing that it's been something that, goes way back to the day where you had that passion at an early age, and we're excited to hear about how that's turned into you becoming one of the foremost experts in our country. So thank you, Miss Jennifer. Robert.
Hey, Pete, great. Thank you for being here. My name is Robert Sears. I'm the director of the NWAVE program. And NWAVE doesn't stand for anything. It's not an acronym. It's actually a play on words. It's NOAA WAVE. So when you think about NOAA and ocean, you have ocean waves. When you think about networking, you have optical waves. So it was a little bit of a play to come up with something that wasn't a acronym jumbo, because we in the government tend to do that a lot, make up a lot of acronyms. I started with NOAA in 2001, actually, in the lab that Jennifer now manages and runs. That was at the time called the Forecast Systems Lab, and that's in the Office of the Oceanic and Atmospheric Research. So I started in research, and that's where I got my passion. I came from the Navy, did 10 years in the Navy. I was did subsurface, surface, electronics, communications. I got into meteorology at the Naval Atlantic Meteorology and Oceanography Center right before I got out of the Navy. That's where I kind of got into computer systems and networking. But I got the passion from the science, the scientists in NOAA. NOAA's mission, and we have a great mission tagline, from the bottom of the ocean to the surface of the sun. That's a lot of observation. That's a lot of data. That's a lot of interconnectivity of scientists, of people, of utilities, of infrastructure. And it needs that vast range of data needs the networking platforms to support that. So working as a junior engineer in the Forecast Systems Lab in Boulder, Colorado, with all these great scientists, PhDs, that made me feel really small, but they, just because of the amount of knowledge they had, but the passion they had about IT and integrating IT and the need of those tools to help enable their mission. So NWAVE, the program that I run, is a government, NOAA, government managed, operated, designed national network infrastructure. It's a carrier grade network. We built it like we were going to build a bank network or any other high available network. It's a high FISMA system. It's a high value asset. We manage the data that goes to the public. So the life and property mission that is NOAA, that life-saving data that Jen and their team produce, travels on our network, and we interconnect that. So the need for highly available, highly secure networking to interconnect these sites is very critical. And our program, the NWAVE program, connects over 140 sites. And we do it from the ground up. We're a full service provider. We go in and we plumb the circuit. We do the routing. We manage the entire thing. And we can get data delivery assurance from end to end. So that data that goes from Boulder, Colorado to the HPC archive in Fairmont, West Virginia, that's all on an NWAVE network that we run, that we manage. It gives us data delivery assurance, that security, and it's also a great business because it's a shared cost infrastructure, and we save our NOAA folks and other agencies that use us a lot of money. So I'm really happy to be here, and I love the passion of this of the team here and the topics that we're going to discuss.
Well, Robert, thank you. And again, some of the things you dropped a FISMA acronym, FISMA, and my producer extraordinaire Hitch in the background might put a reference to those who aren't familiar, but that's an important term, especially when it says FISMA high. And I'll let everybody in our audience learn a little on their own because we're not here to explain every acronym. But you underpinned, or should I say underscored, the underpinnings of how all this works in a world that's become so digitally and ubiquitously connected, Robert. The power of communications, secure communications, pivot here to Ian in a second, that has to be in place in order for that information sharing to occur and to be secure with integrity and so forth, and the speed at which we need that data being served up so that folks like Jennifer Mahoney and team can display graphics and create real-time information for those that are in many cases like public responders and so forth. So thank you, Robert, for that opening. Ian Lee, a little bit more about you, my friend, and also you heard Robert kind of blend in the cybersecurity component because there is one. Floor is yours.
Yeah, that's great. Thank you, Pete. So I'm Ian Lee. I'm a little bit different. So I'm the non-NOAA participant here. So I come from Lawrence Livermore National Laboratory, which is under the Department of Energy. So our mission's a little bit different here. Our focus is primarily on stockpiled stewardship. That's the bulk of what our large supercomputers are focused on. But we also do a lot of other research. So we do work with basic science, basic physics work, a lot of climate research as well actually does get done here. Some large data aggregation services are run out of partnership with Lawrence Livermore. And as you said, Pete and Robert, the cybersecurity of these systems is critical. And the biggest thing there is you want to make sure your systems are up, they're available, they're working well, and they're able to do the science, right? I sit on the division that supports the HPC systems. I'm not a scientist myself by training, but we enable our scientist users to do their science on our systems. So how do we do that in a secure way? How do we allow them to develop the software they need? Our systems are research and development systems a lot of times. And so there is a development of the applications that needs to happen. And that entitles a number of different services that need to be brought in, a number of complex interworking web applications that are needed to host the code, run the continuous integration, the build and test of the software to make sure it's working correctly, that it's giving the correct output, that it's running fast, how to make those performance inputs. And as a lab, we have a long history of putting a lot of effort into these computing resources. A lot of the HPC resources in the US and a lot of the HPC development work by companies in the US is driven by the Department of Energy laboratories and the need for bigger computers to solve larger and larger problems. And so being able to do that in a secure way is very important to us. And we have a little bit of a different situation, right? We're not a distributed organization like NOAA. We're primarily one site, but we do a lot of partnering with other sites. So we have vast compute resources here, as well as at our sister laboratories like Los Alamos Laboratory, which was the site of the recent Oppenheimer movie, if you've seen that, as well as Oak Ridge National Laboratory has large supercomputers as well. PNNL, Argonne, many other sites across DOE have large supercomputers. We're certainly not the only ones.
Wonderful, Ian. And I hope our audience there is taking down that while we have 17 of these amazing institutions, national treasures, shout out, I'm going to see Oppenheimer, I hope this weekend. Boy, what a rich history. And then it's about collaboration. And we'll get to that a little bit as well in terms of how government, industry, and academia are absolutely doing that each day of the week. And as I like to say, twice on Sunday. Again, for our audience, a little more context. We're going to pivot now into some of the technical discussion. I'm going to come back to Jennifer Mahoney. I'm going to launch a poll, though, just to have a little fun, if you all want to take a look at that. Now, wildfires, as we know, is in the news, and we pray for all those who have suffered from, and we're not here to be gloom and doom, but we are also looking at the opportunity that this country has to leverage high-performance computing in a manner to save lives and be prepared for the next one. And oh, by the way, if you're looking at statistics, the National Wildland Fire Preparedness Levels, which there are, I believe, 5, is listed as a 4. And you can go out to, as I look for my notes, and forgive me, it's right here. The National Preparedness Level of 4, you could find this on the National Interagency Fire Center website. And as of, I believe, last night, there are 30, I don't want to give the answer yet, but I think I just tipped everyone off. But net, you all are doing well. Anyway, great resource. Check it out. And if we can go ahead, Hitch, and end that poll in about 30 seconds, maybe not everybody will have gotten the tip or the tell. Jennifer, let's come back because I want to dive a little bit into the coolness factor and all the great stuff that's happening. Ian talked about availability and real-time information, the key to networking. What can you convey to this audience that is, generally from the Beltway, and talk a bit about a deeper dive into the mission and what happens in a typical day and how your data that you are computing and creating and aggregating is being served up to those to make these very, very, very data-informed decisions.
Right. So one of the things that we do, we're developing these high-resolution models. That means we're trying to get forecasts down to the neighborhood scale. So that when you look out your window and you have smoke and fire approaching your house, you have the information that you need as a resident to move and where to move and when to move and to, get out of the way of the impinging fire, for example. What does that mean? That takes models that can run extremely quickly, that are at very high resolutions, that take all of the data that we possibly can get, bring in observations quickly into the models, run the models, and deliver that information to forecasters who can then deliver that information to emergency managers. So that takes a computing infrastructure that is only growing. Our models are getting higher resolutions. We want to go from running a model just over the US to running it over the globe. and being able to then deliver information right at your neighborhood. So Robert brought up the idea of delivering information quickly. We rely on these networks, getting information from us to those that need the output or the displays or the model data. The networking is extremely important just to link all of us together and then run on these really high, these quick, high performance computing systems so that our models can run quickly. So in one case, our high resolution model runs every single hour, and we put out forecasts that go out to 36, 48, and 72 hours. So to do that, and we have to deliver this model and all of that information within 1 hour. So we're bringing in all this data, processing all these models and all of these forecast links so that we can deliver that to the National Weather Service and they can use that to put out a timely forecast. So it requires compute. We never have enough for what it is we want to do because we always want to add more models and more detail, more observations, run it faster, run it at higher resolutions, and that just takes an enormous amount of compute to complete. So in the fire case, we're working right now to add aerosols and different ways to characterize smoke. Smoke is a health issue. And so it's not just the smoke that enters your house, but it's the particulates in the smoke. So we have to bring in observations of all of those particulates into our model that then goes through the modeling process and not only improve the forecast, but also improve the quality of the smoke forecast. And so that we can understand when it's a high smoke day and what type of information and particulates one would be getting if smoke is, entering your house, for example.
So, we're going to come to Robert because this computing thing, I think folks, who are IT, who make products, who sell into commercial and industry, everybody says, oh, the cloud and compute and we can help. And I heard getting information quickly, the criticality of networking, data could be a strategic asset and there's never enough compute. And Jennifer, thank you, because I know maybe we can tap into a little bit more of, and for the audience, think of weather forecasting prediction, machine learning and data analysis, faster response times, fire behavior prediction, wildfire monitoring. There are environmental impacts, when we see a hurricane coming, and this compute, in cloud, on-prem, wherever it needs to be, it doesn't just happen. So Robert, if I may, can you talk a little bit about just that coordination and that there is a lot of work, but some really, really talented folks like yourself and maybe with NWave creating that compute so that the data can be served up?
Yeah, definitely. So high performance computing networking is not your traditional networking. It's not done over the internet. When you talk about the data that Jen was referring to, especially and the key there about getting to that neighborhood level, the more granular the data and observations you can get, the quicker you can get out watches and warnings. That life-saving property that really what Jen and folks are leading in and continuing to try to better. So that research arm of NOAA has supercompute resources in Boulder, Colorado, and Oak Ridge, Tennessee. There's a grant with Mississippi State. We have our geophysical fluids dynamics lab, GFDL, there's an acronym for you, in Princeton. Another, you're watching the Oppenheimer movie, another groundbreaking area of intelligence and innovation. Those are the research compute facilities, and they all need to be interconnected. Then we have NOAA's operational supercompute. So the research arm is continually improving and bettering those forecasts. The Jen talked about the high rapid resolution refresh model, the HER. That was a game changer in forecasting and warnings and getting that granular data. But that meant a huge jump in that in the amount of data that needed to be processed and moved around the country. You don't have a supercomputer in everybody's basement, right? So you got to connect scientists, and sometimes globally. The lab that Jen leads has folks working from all different disciplines across the world to continue to better those. So it's, you have to link them together, but the data that itself, interconnecting those supercomputers, needs a highly available, high capacity network. And this is one of the reasons why NOAA built its network. And the NWave backbone is a 400 gig backbone. So when you think about your home network, and some folks that are in really good areas may get a gigabit. 1 gigabit is pretty darn fast for a home network. And you think 400 times that is what the NWave backbone is. So we can move data from those supercomputers, whether it's moving the raw data from the research side and over to the operational side, or archiving the data, which is another big piece. You know, you create all these models and you run and you get the data to get the results. You got to archive that somewhere too, so folks can then scientists could then call it up at any time, and we do that in our Fairmont, West Virginia location. So this backbone then connects to these supercomputing facilities. The Boulder, Colorado facility, where Jennifer is that has 400 gig connected capacity. So does the the operational compute that we have in Phoenix, Arizona, and in Manassas, Virginia. They have to have that high availability, or sorry, that high capacity is one thing, getting the big bandwidth to move big data. You then want the reliability, because that and the availability of that network, because you need that data to continuously move. It can't be down. You need almost 100% uptime on the network to ensure that data moves. So when we talk about high performance computing networking in an IT environment, it's definitely a bit different. The disciplines are different. You don't just plug in machines and away they go. You have to tune your systems. A compute node, a server out of the box is not optimized to move data and use a 10 gig NIC, a network interface card, a 40 or even 100. There's things you got to do to the TCP/IP stack to get that to work. So there's all these disciplines that then make that compute work, make them move fast. And then when you're running your own network, like we do in NWave, data delivery assurance, moving data from Boulder, Colorado to Manassas, Virginia. If you have that network like we do today, every node on that, every router on the hop from Boulder to Manassas is run by our team. That means we know where every packet's going. We can tune it. We can ensure that data is delivered. So that is something to consider when you're building high performance computing networks. Is it needs to be highly available, highly reliable, and secure, to also protect that integrity, because you don't want to flip the bits on things that are dealing with life and property, and you got to make sure that goes through seamlessly. And lastly, I'll say one of the things that NOAA really has embodied myself and my team, working with the science and working day to day in that protection of life and property, is IT is an enabling factor. IT should be an enabling factor. Many times we see IT as a cost center. It's just it's a cost of doing business. Our program NWave has changed the game for a lot of our science. We're saving money because we're running a shared infrastructure. We're putting that money back into science. But we're going from, say, well, I can only afford 100 meg a gig. Well, I'm going to give you 10, 100. What can you do with that? And every scientist can always use more bandwidth, and they will use it.
Wonderful. Thanks for painting the picture. I'm seeing some head nodding. So I'm going to jump to Ian, then Jennifer, please. If there's a comment, you could just cut me off and say, I want to riff off that for a minute, what Robert talked about, because we're going to get into a segment on collaborating, not just within NOAA, but across government. I'm going to put out there for the audience that, we're going to refer at times to R&D and science and research, but look, Department of Energy, National Science Foundation, Department of Commerce, the National Labs, there's Department of Defense. Since 2021, 3 pieces of legislation have been passed, known as the Bipartisan Infrastructure Law, CHIPS and Science Act, and the Inflation Reduction Act. And baked in there is a statement, or should I say, it addresses the introduction of $2 trillion potentially in new federal spending over the next 10 years in a world that is dominated by an Internet of Things, an industrial Internet of Things, and a connected world. The devices we carry and assume are protected may not be. And to Robert's point, HPC is purpose-built. It does still depend on the same things any network would. Reliability, resilience is a word that is often used in the critical infrastructure domain, but also being 100% up and IT is not the problem, but it's an enabler for the information we need. So Ian, when I hear about all this connectivity, kind of geek out a little bit for us on HPC and cyber, where we are today and kind of the things we look at for purpose-built platforms like HPC.
Yeah, and pulling it back from just cyber as well. a lot of the things that Robert and Jennifer mentioned resonate a lot, right? So Robert focused on the network. That's where he's focused on. For us here, there is a lot of that system software, and there is a lot of that making use of the large computers. So our use case is a little different. We're on one site, 1 square mile is Lawrence Livermore. So most of our data does not have to travel very far to get to the computer. So we've kind of avoid some of that problems. We do have fat interconnection pipes, 400 gig or large, also large, similarly large connections out to our sister labs to move large amounts of data and do simulations at other sites. For our local compute, then it's a matter of bringing as much compute resources to that data. So now that we have the data with that we want to do our simulations on, how do we bring the most compute to that? And I wanted to use this one, kind of bringing it home sort of message. This is one I picked up from one of our past leadership. So we throw around these numbers in HPC, and they kind of get to a point where they're so large that people don't really understand them. So if you look at, and I know I'm segueing or foreshadowing a poll you have coming up, but when we look at something like the top 500 list, which is the big, ranking worldwide of supercomputers, Lawrence Livermore shows up on it a number of times. The US in general shows up on it quite a lot. NOAA has several systems on there as well. You'll see these numbers like teraflop or petaflop or nowadays exaflop, right? And these numbers, they're like, okay, it's a big number with a lot of zeros after it. But let me try and bring that home a little bit. So right now, according to Google, the world population is 8 billion people, approximately. And a petaflop is 10 to the 15 flops. So it's a 10 to the 15 calculations per second. So a 1 followed by 15 zeros. And so what that really means, right? If you want to kind of think about this in human terms, is if you had, for 1 petaflop, if you had every man, woman, and child on Earth grab a calculator and start punching in, 1 plus 2, 2 plus 3, etc., they would need to do that 1 calculation every second for an entire day and a half just to equal 1 second of time on a 1 petaflop computer. So then when you look at, like our current largest cited system here at Livermore is Sierra. That's theoretical peak is about 125, rated peak is about 100 petaflops. So you're looking at 144 days of computing time, of humans punching a calculator computing time every 1 second on that computer. And as we move to exascale, right, that just goes up from there. So an exaflop is 10 Sierras, basically. And so that's, 1,500 days to get to 1 exaflop of compute power. And so you start to get kind of an idea of what the numbers are that we throw around and what these things mean. So
go ahead, Ian.
And so what that means is to Robert's point, right? A lot of the things that work on your home network or your business, standard IT network don't work at the scale of HPC. And so Lawrence Livermore, in getting to the collaboration topic as well, is Lawrence Livermore in particular has had a large history of developing software to make our HPC systems run efficiently, right? We've been buying these systems and deploying them and wanting to make the most of them. And we've had to develop our own software or work with vendors and partners and other universities, other agencies to make that software better. And a lot of that we actually put out as open source software. So this is getting into that collaboration, right? Where do people collaborate on various pieces? Open source software is one of the ways we do that. So a variety of applications and software, underlying system software that we've developed here is actually available for the community for other HPC systems and for NOAA and for general users. A good example of that, right? Kind of a concrete example. Some of the more technical people in the audience might understand this. There's multiple different ways to set up a file system, right? When you have your file system at home and you have a hard drive with a terabyte of data on it or something like that. There's standard file system types, and one of the big ones that we produced is ZFS, and that is actually an open source project, and that's actually incorporated into regular operating systems that you can just go install. Ubuntu started adding in like 2016. So that software does flow out.
Yeah. So Ian, and again, for the audience, that was a very, quick and dirty, like lots of terminology is part of what we're trying to do. And that's, understand flops versus, cybersecurity versus encryption. There's just a lot. And I see Jennifer has her hand up, but Jennifer, go ahead and jump in. I just wanted to say, Ian, Thank you for introducing a lot of buzzwords, and the people have to understand how complex these systems are. Jennifer.
Yeah, I thought I'd take this opportunity to just kind of build on that. From a research standpoint, with all this increase in, flops and teraflops, it also takes science. So there's a science aspect that has to occur to utilize all of this amazing technology that then finds its way back into the models and how we develop models and deliver models. So we can't just take a model and go, great, we're going to put it on an exascale system. We have to actually do the science of the high performance computing, linking that to our model development that gets us back to, using these great technologies that Ian just pointed out.
I appreciate that. And hey, in the spirit of digital, if you have a question, if you could direct them through the chat to the person, that would be great. I'm not fully vetted on these emoticons, but it looks like if you raise your hand, your face is going to come up. And if you don't mind, no disrespect to the wonderful Paula Gold-Williams, I didn't see that coming, but please ask the question through chat. That would be awesome. Jennifer, thank you. And again, I want to come back to just closing out. Ian, you went in a great direction. The complexity of not just building these platforms, and then as Robert pointed out, communicating across them to get the data on the GSL platforms that Jennifer oversees. We got to make sure that data is secure. We have to make sure that some of the guidelines that our friends at NIST and other places put out that apply to desktops, they apply also to protecting that data, but there is definitely cybersecurity considerations that are probably unique to HPC, and having that open source community to kind of dive into that is something that, yes, we'll get to here in that collaboration realm. Robert, did you have any kind of closeout before we move into the people process technology realm?
I guess I'll just add, and sorry, I had to do a wardrobe change. My AirPods decided to flake out, but look how fast that was. You didn't even notice.
You're the man.
Yeah, the technology shifts and changes. One of the things, and on the topic of climate, we've seen as that exponential growth in compute power and networking. When we started NWave, we had a 10 gig backbone, and it took about a half a rack of, in a compute rack, there's 42 rack units, maybe it's an 8-foot tall rack. Half of that rack was the router that needed to interconnect that backbone. Today, on a 400 gig network, we have 2 rack units for the router that is interconnecting our backbone. The size, and this goes to the technology. This also goes into, I'll just throw in a plug for the Department of Commerce, trying to, under the CHIPS Act, and that's something maybe something could pop in there, moving chip manufacturing back to the US, and that drive there, that the amount of power that we've put now into our devices, the technology just in the past 10 years, going from a half rack to this minute small footprint of power. And the same thing's happening in the compute side, right? It used to take, a whole room full of compute to get to now what maybe is just a few racks of compute power. And now that smaller footprint equals a smaller burden on power, less, you're using less power, less cooling. There's new technologies for how you can do cooling, because as that technology increases, the more power, the footprint goes down, the more you can pack in. We're seeing in data centers, in co-location facilities, that decrease of power, and again, that carbon footprint that gets created. So there's this other side of the technology that is got a benefit through innovation, through that form factor getting smaller, and the more power you can pack in, it means the less consumption of energy. So that's a whole nother part of the technology that we're seeing that's kind of helping towards limiting that carbon exhaust, because you have a supercomputer that's doing climate research, it's doing fire weather, you're putting all this stuff in, but it's also, creating its own carbon footprint, right? So there's this balance, and we are trying to be good stewards of what we do and back that with the technology. So just something to add there.
Yeah, no, let me put out there, folks, Executive Orders 14008, 14030, 14057, in addition to some that predate, are just ones that come to mind. If you want to take a look at those, they are related to, footprints and carbon free and just statistically, what generates the more compute, the more power is needed. And obviously in a world where distributed energy and fossil fuels are both needed, we're using more energy to produce more data, and HPC is is an awfully big consumer of that energy. So we're always looking at how we can, get to that low carbon footprint. Thank you for that, Robert. We're going to move now into something I hope our audience will appreciate, is the collaboration component. We often hear about people and process and technology, open government tenets of being, participatory and collaborative and transparent. I'd like to talk to Jennifer, or each of you can address, how do you do that, right? You're reacting to wildfires in many cases, or some environmental impact. How do you build in that time to meet with industry about, whether it's a new product or a capability, or just make time to learn from those making products and solutions that could make for a more reliable, resilient, HPC underpinning, or serve up data in a manner that gives us much more richness to it? Jennifer?
Sure. I want to go back to the fire weather example and just start with, 2 years ago, we had a very significant fire that came through the community here in Boulder and several of the outlying cities. One city was my city in particular. And after that event, we had our politicians, we had emergency managers, we had our forecast office, the research arm of NOAA, and our satellite group from NESDAS all get together and think about what happened on that day. And what came out of that is, what tools do we need to build this collaboration, to engage our emergency managers, to make sure that the forecasters have the right tools and technologies in their hand. And this collaboration is so important, not just with the emergency managers that are on a, during an event or during a fire, but all of those external communities and businesses that are developing tools for fire and bringing them to the table. So one of the things that came out of that, and talking about the bipartisan infrastructure law, one of the areas we're focused on in GSL is building a fire weather test bed. And this test bed is exactly meant to bring the communities, the interested parties, people developing and interested in fire together in one place. Because after this fire occurred and we all sat around the table and talked about solutions and gaps and decisions that were made, only knowing that will help build and deliver the tools that will then fill those gaps. So the fire weather test bed is starting. We're starting to bring in some capabilities, but I really want this place to be open and broad. And that's where we can bring people to the table and talk about particularly the fire problem.
I love it. And folks, Jennifer Hitchcock in the background is putting up amazing links for where these resources are. I know our industry partners, having been in government for 25 years, it was, hey, can I get a meeting with Pete Saronis or Jennifer Mahoney or Robert Sears or Ian Lee? There are ways to do it that isn't you having to come in and sell something, but to be a part of something like a fire water test bed or fire weather test bed. So thank you. Robert, let's go to you. Open government. How does that work in your world with engagement, collaboration, and meeting with industry to kind of hear the innovation happening outside the walls of NOAA?
Yeah, definitely. So that's a very timely question. I'm actually, you may not know it today, I'm in Irvine, Texas. I'm at a Verizon headquarters at a Defense Research and Engineering Network technical interchange. So one of the things that we do in our program is collaborate a lot with our other federal agencies that are in the same kind of boat as we are when we talk about high performance computing, networking, having to build networks that can have this capacity, the resiliency, the data delivery assurance, all that. So DREN, Defense Research Engineering Network, is one of those key. So there are a lot of folks in that group that work directly with, which then ties us into some of their partners, like with Verizon. We also work with Energy Science Net, ESNet, under Department of Energy. They're a great they're tech leader when it comes to innovation, and have set a lot of great standards for how you do high performance computing networking. So there's that collaboration there. And then just what we do within our science research and education community, because they're also leading folks like Internet 2, regional optical networks, universities. I'll just give a shout out to University of Maryland, Max Gigapop, our friends up at Pacific Northwest Gigapop. These are folks that have the same type of issues that we have, where it's a lot of data. They need to collaborate and intercommunicate, so they start to build their own infrastructures, which means we're going to non-traditional partners a lot of times. Dark fiber owners, folks that'll lease you dark fiber, the leading edge of optical networking, who's doing that. Coming up here in November, supercomputing, SC23, that'll be in Denver, Colorado. There's gonna be a show floor full of the latest and greatest when it comes to HPC and networking. So those are the places you wanna go. So folks there on the, that are out there in the Beltway, go to SC23, just Google that. There's a group called SciNet. They're the group that builds the network for supercomputing. It's the fastest network in the world for 1 week. And it's to deliver the required networking resources to the show floor. And they're doing terabit level network. So not the 400 gig backbone that NWave has, but 3 to 4 times that. And it's all done through volunteers. Volunteers from the community. I have 4 staff from NWave that are going. They're going to build like the wireless network. They're going to build the wide area network. They work with vendors that donate the hardware, and a lot of the vendors will do their best and brightest. They'll have their newest products, and they'll all interoperate. So you'll have the Junipers, the Siennas, the Ciscos, all that come together to build the fastest network in the world. And it's an amazing thing to see. So I'll give a plug to our SciNet folks, but that's that collaboration you have to do. And if you're an IT practitioner within the federal government, you need to look outside of your agency, look outside of your local group, because there's a lot of resources there that can really propel you for what you do. And one thing that NWave does for our community is peering, and it's a technical term. It's both technical and makes sense. You have your peers, your direct people you work with. We do that same thing in networking. On the perimeter that is NOAA's external perimeter, that security perimeter that then connects to the world, we peer with the internet. Yeah, we have internet connections, but we also peer directly with universities. We also peer directly with other agency networks. So data doesn't have to go up to the internet and bounce around and come back down. It goes straight to folks at Lawrence Livermore, because we do peer directly through a group called the Western Region Network. So there's technical ways to reduce the hops. How many hops does it take to get across the network to get to your destination? Reduce that through technical means of direct peering. And that's something that we do. And a lot of times folks don't see it. But when things do break, of course, they see it, but they may not know that the path is optimized to get to very specific data. So that technical means of peering is a big thing.
Great. And let's pivot over here to Ian about, this collaboration. You mentioned the open source, but, I'm hearing, and I hope our audience, those who, again, sell into the government, it's sometimes good to have the conversation, to do the homework, to research the capabilities and the tools and so forth at places where Jennifer and Robert, and of course, Ian, you work. So I like to preach, do a little of that homework to come in and have a conversation about you and your mission to help support or advance, in this case, HPC science and research and development. So thank you for, again, expressing that open government's in full effect at NOAA. Ian, your thoughts on the open government principles?
Yeah, so actually how I got into cybersecurity as a focus, right? I have a background more as a software developer, and I actually got in kind of with GPU computing when that was becoming a thing in around 2010. That's what got me to the laboratory initially. But actually, open source software is how I got into cybersecurity by way of several of the government acts, the executive orders, some various OMB memorandums. This is actually where you and I met the first time, Pete, was talking about how to collaborate on cybersecurity approaches that we all have to meet. So for instance, if there's a new government-wide mandate for, at the time it was website security, HTTPS security, building tools that allow cybersecurity practitioners like myself to be able to know whether we're in compliance or out of compliance with these orders, as an agency like CISA is trying to coordinate and make sure all the agencies are secure. open source has been a really powerful tool for that. I'll echo what Robert says. So supercomputing, I put the link in chat, is a great event. I'll be there this year, and we have there's a supercomputing held workshop on cybersecurity. I believe it's at the front end of the week this year, and that is a chance for folks from all across industry, academia, the national labs, other government agencies to come together and talk about their concerns, to talk about the sort of unique risks. As we pointed out, there's unique challenges with HPC systems, and it's an opportunity to come together and talk about them more throughout the year as an ongoing thing. And actually, the folks that are kind of hosting or organizing that workshop, NIST actually runs an HPC security focused working group. So we had just in March, we had our third workshop, got together, talked about what various different organizations are doing around cybersecurity of HPC systems. And again, that's a NIST working group. So that's not just DOE, that's DOE, military. I don't know if NOAA was there specifically, but folks from all over government, academia, there was industry folks there as well. Is it an opportunity to come out and collaborate together on these problems?
So I love this. And again, please, anybody listening, our attendees, you have places you can go and now say, hey, if you're at Supercompute, there's Ian Lee, the dude with the ponytail who's awesome. I seriously doubt Ian's going to say, I don't have time for you. But this kind of education, this kind of opportunity, maybe you have to get on a plane, maybe you don't. You'll probably have Ian's contact information. You could see and feel the passion from these individuals. And I just hope that, this segment of the discussion shows you can't say people aren't approachable if they're telling you there's opportunities to come together with purpose. So thank you for that. I'm going to introduce, or my colleague Hitch is going to introduce our second poll just to have some fun. And I will go ahead and do it. No, it looks like Hitch has done that. Go for it, folks. There is a poll out there that we hope that you all will have a little bit of fun with, and then of course we'll share those results. Jennifer, any thoughts on anything before we hit the part where I think I'd like each of you to ask and put on your visionary hat for a minute and just talk about the future, the art of the possible, something to get people excited about in terms of with all this going on. And yes, we're fighting fires and addressing droughts and things on a daily basis. And let's give a shout out to all the personnel who are out there doing it, risking their lives. What's something that you're excited about, say, over the next year, or that you can leave with the audience?
Sure. So one of the things kind of building on this collaboration is we're building a unified forecast system. And this unified forecast system is taking the latest and greatest models and opening the code to community development. And I think if you're into model development and extending and expanding and building on these models, it would be through this unified forecast system. And we also are really thinking forward with respect to building the latest models with some of the funding that you mentioned. Models that can take in all constituents of air chemistry and air constituents so that our models can produce more accurate forecasts of air quality. Fire behavior, we're linking with some of the other research organizations to bring fire behavior to the National Weather Service. So there's a lot going on in our modeling, opening up our community and making NOAA have the best models in the world by using all of the knowledge that we have to make those systems, high quality and moving forward as far as their accuracy and resolution. So, and just one other point I wanted to make is it's great to have both Rob and Ian talk about all the great work that they do, because as a scientist, I don't worry about any of that. And if it weren't for them, we wouldn't get our job done. So thank you. I just wanted to mention that.
Jennifer, that's huge and awesome. And I love it. It gets me all fired up as a citizen, resident in this country, that there's just that passion and appreciation. Robert, I'm going to come to you, but let's, again, for the audience, again, we're focusing on, HPC as an enabler. Wildfires are one type of impact, but at the end of the day, in this case, we're developing new technologies for fire modeling, fire detection, fire prevention, fire management, fire recovery. If you all out in industry do that, not, just, yes, we're a great tool that does AI and machine learning, and we can help you with data insights, you got to distill down to some specifics for folks like this who are and can be champions for your innovation. So I just want to echo a lot of what you brought up without being so specific, but you're in a constant state, Jennifer. I heard of we're always trying to transform and learn. So, from industry. Thank you. Robert.
Yeah, and I'm really thankful that Jennifer, said what she said about what we do for the IT infrastructure and how we enable their science, and because that's really why we do it. That's really what got me excited about coming to NOAA. And 10 years in the Navy, I think I've done more in NOAA in the first 6 years that I did when I was serving in different campaigns when I was in the Navy, because I could watch the growth, I could watch the innovation that's going on. And I think every citizen should really kind of research and understand what these agencies are doing. It's your taxpayers' money, it's your money at work. We are all, I know Jennifer is, I know Ian is, good stewards of the taxpayer dollar, and we really want to continue that innovation. So, research the science, know what's going on, because this work is saving lives. That's what it's there for. You watch the news and you see the forecast. That's NOAA forecast data. That's NOAA data. That's the work that Jennifer and team do, and that's really the great part about being in these type of organizations. The things that's getting me excited is one of the things that I get to do in my position is not take for face value what's available. Meaning, if I go to a region, if we go into a state and we're looking for networking, we're looking for things to increase capacity, and it's like, well, this is all we have. You buy what you have, that's it. Well, I don't like to take that as an answer. It's like, okay, well, then we're going to build something better. We started a group called the Alaska Region Technology Interchange Committee. It is a NWAVE sponsoring it, but it's a voluntary organization of universities, tribal, state, federal government. We're meeting in September. We do this every year, and then we meet monthly. How to better broadband in the state, how to better access to data, how to build infrastructures that impact not only federal agencies, but the community. And this has been I think we started about 3 years ago, and now it's really developed. We're going to have a great meeting of minds and talk about what people are doing. What are the challenges? Alaska happens to be one of the most underserved state when it comes to broadband, but it's a lot of it's an epicenter of climate action right now. We have ice melt that's happening up in the Arctic. We just had a big fiber outage that was done by a ice shear that fell into the ocean and went, I think it was like some 30 feet into the sediment, and cut a fiber line that served the entire the northern part of Alaska. This is climate change. This is what's happening. This is ice melt. This is what our scientists are doing to do prediction. So it affects us in all sorts of different ways. And you look like you want to jump in.
Well, I'm just, this is where I'm like, folks, wildfires, ice shelves, physical infrastructure impacted by events. We hear cybersecurity. Physical security usually will kickstart falling lines, sparking from, the brush that has been arid because we haven't had enough moisture. I mean, when you cut a line in an undersea cable, for example, just using one, stuff shuts down. When someone, Colonial Pipeline takes over, then we realize what we depend on every day. So thank you, Robert, just for that. And Jennifer, these 4 examples as we look to mitigate risk to wildfire, but boy, can high performance computing, sorry for jumping in, I just got all passionate about, just learning how to do and predict better and mitigate loss of life. Ian.
Yeah, that loss of life is obviously very important, right? Another example, you mentioned the Colonial Pipeline. When some of the work that we've done for cybersecurity for HPC systems is also on the research side. So not just looking at how do we protect our systems, which is very important. How do we keep them up? How do we keep them working correctly? It's a big IT problem, but also how do we use these systems for cybersecurity, right? Branching out from just wildfires, there's also tie-ins to things like power grid security. When you look at some of the power outages that have happened over the last decade and the cascading effects that those can have, the security of the actual infrastructure is also of very high importance. And of course, Department of Energy, right, that starts to come back into our camp a little bit. I wanted to tie back to something that Jen said, both kind of now and a bit earlier, about these systems and how much the scientists want to make use of them, right? She made a comment earlier that was to the effect of, there's always more bits that you can add to your model. You can get finer grain, you can get down to that neighborhood level or the individual house level. Or what you might want to do is might want to add more capability, more particles, more variables into the equation. And that's what some of these larger and larger systems, which inherently cost more and more money, there can be some question like, well, what are we doing with these things? And I just want to dispel any confusion there might be that these systems, at Lawrence Livermore, at any of the labs that I've ever talked to, at NOAA, from what I understand, they're all utilized all the time. They're fully loaded, as close to 100% time as possible. 90+% is very, very common. Of course, you have things like drive failures and regular, like my computer went bad sorts of problems, which when you have thousands and thousands of nodes working together, you just have a higher chance of that happening in the middle of your simulation. How to be resilient to those sorts of challenges is also very important. But as we gain these bigger and bigger systems, right, and something like El Capitan, which is our biggest system we're in the process of landing right now, is expected to be somewhere on the order of more than 20 times what our current biggest system is. And that system, I would expect, fast forward into its lifetime, it'll be used full time, right? It'll be working around the clock, doing the science that needs to be done.
So let me punctuate. These supercomputers, if I'm hearing you correctly, and dispel that, they're not sitting around idle. They're being used. So if you need to get on them, get in line. But again, it just hopefully, as again, those listening, this is the science and the energy and the power and the compute to hopefully make it safer down the road for generations to come. Awesome stuff, Ian Lee. I want to just say the polling, hope you had fun with that, folks, because everybody generally got right answers. The majority did pick out, it was 5 supercomputers in our current, as of June, top 100 are United States, and then the wildfires, 37,706. So thanks for taking part in that. Jennifer, Robert, Leanne, my favorite part, it's 11:57, just to kind of bring us home. Parting shot. What do you want to leave with the audience based on what we covered today? You heard from your colleagues, and leave with the audience so that they can walk away feeling like I want to learn more.
Sure, I would say that it takes all 3 of us to make a forecast for your neighborhood. It takes the science, it takes the computing, it takes the networking, and the security. So all of that together is what brings life-saving forecasts to your door, basically.
Wonderful. I love it. Tweetable, folks. Robert Sears.
Let's see if I can come up with some good taglines. For those in the private sector, don't sell to the government, enable the government. That's what we really need to do. We need to look at technologies that enable. We're all citizens here. We're all taxpayers. Look at the technologies that will enable to keep America moving forward with technology, with our federal agencies being the best that they could possibly be with technology at hand. Put my hat on for the chair of the IPv6 task force. IPv6, we need our products to be able to, work in IPv6, and that's where we're moving as far as from an IP perspective. So I have to throw that out there, or else the chairships will get mad at me. And then those in government, like myself, we talked about it, collaborate, get outside of your agencies, get outside of even your division, see what's going on, go to these meetings like supercomputing, talk with your colleagues, because there's a lot of work that's going on. Somebody's doing something you're doing, or you're doing something that somebody else wants to learn. If we can continue to collaborate as federal agencies, that will make us even stronger and even better organizations.
Love it. Love it. Love your passion, Robert. Excited to work with you moving forward on our community as we build it out. Ian, parting shot.
Yeah, I mean, Robert's closing thought there of get out there, collaborate with your other agency partners, figure out, if you're like me and you're on the security side, you often get a bad rap for just being the person to say no. But generally what we're really trying to do is how do we enable that science to happen, but in a secure way that actually keeps things up and working and available for everyone else. Get out there, figure out what your users are doing. If you're a user of an HPC, if you're someone like Jennifer on the modeling side, learning how the actual hardware works is super important. And to vendors, I would say, right, the advice I got early on in my career, seek first to understand. HPC, as you've heard today, is a little bit of a different beast. And what works on enterprise IT probably doesn't work out of the box on HPC. So coming in and saying this thing will solve your problem is going to leave us very, very skeptical. And trying to understand, how is HPC different? How does it fit in? Not to say that there's not partnerships to be had there, but just come at it a little differently.
Thank you, Ian. My parting shot is one, just thanks and gratitude and appreciation to each of you and our audience for participating. I want to hear more from you. I see my colleague and producer extraordinaire, Jen Hitchcock, putting in some links there. What didn't we talk about? What can we talk about in our next segment? We are going to be releasing and working as a community here in the HPC climate working group / working with industry and coming up with material and content, both digital and written, to educate the masses. Follow Dots and Bridges, if I may, shameless plug, on LinkedIn and X, formerly known as Twitter. We want to continue this conversation around technology, which underpins our most critical sectors in the country to benefit humanity. So again, thank you. We will be in touch again soon, and have a wonderful rest of your day.